Okay, hello everyone. Present this paper called Rearchitecting the Linux storage stack for microsecond latency and high throughput. It's from these people at Cornell and UT Austin at this year's OSDI. So the main sort of question this paper asks or tries to answer is, with the current Linux storage stack, can we achieve sort of microsecond scale tail latency? And what the authors state is that a commonly held belief among a lot of papers and people is that it can't achieve this because it's too sort of general. And there's two sort of main reasons why people might argue that. The first is that as we have all these new devices, you know, fast NVMe SSDs and fast memory, persistent memory and stuff, the CPU overheads in the Linux storage stack are sort of too high for us to achieve the latency of the devices. And the second argument is that when we have these multi-tenant deployments where lots of different users are perhaps sharing a device or something, it's very hard to achieve microsecond scale tail latency because we have to be fair to everybody and it's very general. So the main issue they try to solve in this paper is that the reason a lot of the time we can't get these microsecond scale latencies is because the latency sensitive apps we care about compete with throughput apps at the same queues. And throughout the work, they refer to these latency sensitive apps as L apps and the throughput apps as T apps. So just as an example of the problem with these L and T apps, we have two graphs on the right. And the top graph, for both of these graphs, what we do is we have one throughput sensitive app and we vary the number of latency sensitive apps. And what we compare is Linux SPDK and a setup called SPDK priority, where we give priority to the threads with the latency sensitive apps. And what we notice is, in terms of latency, this is the average latency, when we increase the number of latency sensitive apps, the latency increases for all cases. And when we look at throughput, in this case, throughput per core, when we increase the number of latency sensitive apps, in general, the throughput will decrease, sometimes more than others. In particular, for this SPDK priority case, throughput almost completely drops when we situate a latency sensitive app with a throughput sensitive app on the same core. And there's three sort of different reasons for this. For the Linux one and the SPDK one, the problem is called head of line blocking, or HOL. And for the SPDK one, the problem is that polling can actually increase tail latency depending on the setup. And when we use priority for threads, as in this SPDK example, the throughput apps can be starved and never get requests. So we can go through some simple tests to demonstrate these things. The first is head of line blocking. So in this test, we are measuring the latency of a sort of latency sensitive app while we use an app producing a lot of throughput. And what we do is we increase the IO size of the app producing the throughput and measure the tail latency of the latency sensitive app. And as we might expect, when the IO size of the throughput sensitive app increases, so does the latency of so does the tail latency of the latency sensitive app. And the reason is because when latency sensitive apps compete in the same queue as throughput sensitive apps, these latency sensitive requests need to wait behind the large throughput requests, increasing the tail latency. So the second sort of problem is that even when we use pooling, tail latency get worse. And the problem lies in the interactions between pooling and the CPU scheduler. So the main issue is that when we use a scheduler, for example, completely fair scheduler. Threads are given time slices of when they can run before they are preempted and another thread runs. And the problem is that when we initiate a latency sensitive request at the boundary of a time slice, so right when the time slice is finishing, we need to wait until the next time slice of the thread before that request can execute, which increases the tail latency. And the problem just gets worse as we have more apps competing for the same core. So it gets worse in two ways. What happens is that when we have more apps competing for the same core, each app gets a shorter time slice, which means that a higher percent of the requests have to wait for the next slice in general. And then once we increase the amount of apps too, not only do more requests need to wait at the boundary for the next slice, but we just need to wait longer in general before all the other apps finish their time slices. So if we look at the graph on the right, we measure the time period that each thread is given, and we increase the number of latency sensitive apps. So at the beginning with just one app, we sort of run and wait for the same time, but as we increase the number of apps, the scheduler gives each one a smaller time slice. So we have less time to run in this checkered bar, and we have more time to wait, which increases the tail latency of the app. And the third sort of problem is that we might think a good idea is to sort of prioritize these latency sensitive apps, using Linux prioritization or whatever. So the theory is that if we prioritize this application by reducing its niceness value, for example, maybe we can get lower latency. But the issue is that when we prioritize apps like this, or prioritize threads like this, what tends to happen is that the throughput sensitive apps just don't get any requests served at all. So on the right, the top right, we have a graph where we have in purple, we have the average latency of a latency sensitive app. And in blue, we have the tail latency. And then in red, we have the throughput of a throughput sensitive app competing for the same core. So we'll notice that at a niceness value of -20, which means that the latency sensitive app is being prioritized, the average latency and tail latency are very low, which is what we want. But at the same time, the throughput sensitive app, the throughput is almost zero, because every time the latency sensitive app is being prioritized and the throughput sensitive app just can't continue. So as we decrease the niceness value of the latency sensitive apps thread, throughput starts to increase, which is good. But as we notice at the same time, once throughput reaches a certain level or a certain amount, the tail latency and the average latency of the latency sensitive app starts to increase, which we don't want. Another thing we might try is we could make the latency sensitive app sleep for a short amount of time to allow the throughput sensitive app to progress. And on the left here, we have, on the bottom right here, we have the sleep interval of the latency sensitive apps thread. And at the beginning, we don't sleep at all. We just see the same problem. The throughput app can't progress because the latency sensitive app is taking up all the time. But as we make the latency sensitive app sleep more, the throughput increases for the throughput app, which is good. But as we see again, the tail latency and the average latency just increase for the latency sensitive app. So neither of these is really a solution to this issue. So in this paper, they introduce a modification to the block layer called block switch. And their insight is that the queues in the block layer for each core are sort of conceptually similar to network switches, where they might switch requests to different places to balance load and latency and stuff like that. So they introduce what they call a switching architecture to the Linux storage stack. And the general idea is that instead of requests from cores always belonging to the same queue belonging to that core, we can direct these requests to other cores for load balancing and latency prioritization. So the idea is that we can prioritize latency sensitive apps on their original cores or we can move them to other cores while we direct these throughput sensitive apps to underutilized cores. So just a very brief overview of what the block layer looked like in the past. We would have multiple CPUs, but all the requests submitted by these CPUs would go to the same queue. And maybe for a while that was okay when devices were kind of slow, but as devices got quicker, we have a lot of contention on the same queue, and we just can't fill the queue depth of the new devices and can't extract as much performance as we wanted. So recently, there was a modification to the Linux kernel called block multi-queue. And the way it looks now is that we have these CPUs submitting to per core per core request queues in the host, and each of these queues has a queue to the device, which was good in that it sort of resolved this problem where we had all this contention on a queue. But at the same time, it doesn't do anything to solve this head of line blocking issue that the paper talks about. So what they introduce in this paper is block switch. And instead of just one core having one queue per device, what they do is they give each core multiple queues. So we have one for each class of application. In this case, each core has a queue, 2 queues on each device, one for a latency sensitive app and one for a throughput sensitive app. So if we look at the diagram here, in blue we have core 0 and in red we have core 1. And core 0 has these sort of 2 software queues in the block layer, but it has 2 queues on the SSD and 2 queues on the network card. And likewise, core 1, we have 2 queues in software and then 2 device queues connected to each device, and one for latency app and one for throughput app. And in general, in this scheme, we prioritize the threads for latency sensitive applications over throughput sensitive applications, which kind of sounds like the problem we just introduced at the beginning, but as I'll explain, the design is quite different, and it allows them to sort of sidestep this problem. So the first scheme they introduced or technique they introduced is called request steering. And the idea is that when we have some queue that is congested or it's full or something like that, we can, instead of the requests being tied to the queue they were originally submitted, these requests can be directed to different queues. So if we look at this diagram, we have core 0 submitting requests for a latency app and a throughput app. But the original queue assigned to this core at the network card is full. So it has 3 little orange boxes here. So instead of this request just waiting, because this queue is assigned to this core, the request is instead directed to the core belonging to core 1. So in this diagram, in this example, these queues were underutilized. This core was underutilized. So the request is directed to a free queue. And this is called request steering. And request steering is, it's aimed at solving sort of bursty or transient high load. So we sort of prioritize latency sensitive requests, but if we have congestion in the queue for a throughput app, for example, we can just steer these requests to a free queue on another core. So the important point is that unlike the current block layer in Linux, we are not tied to the queues originally assigned to our core. We can put requests in the queues for other cores, which is the steering part of the scheme. The second part is, instead of request steering, there is application steering. So request steering is good when we have sort of transient load or bursty load, and because we don't need to steer that many requests, hopefully. And so the overhead, there will be some overhead, but it won't be too much. But if we have some persistent load on one core, every request for a long time needs to be steered, which introduces too much overhead for context switches between cores. So the second technique is application steering. So in this example, the throughput app on core 0 had heavy load, but it wasn't sort of bursty or short. It was persistent and lasted for a long time. So what happens is that the block switch at the block layer moves this app to the next core. And the benefit of this is that now the request from the throughput app can be directed to its queues without any request switching, so without any overhead. So the block switch in the block layer recognizes when we may want to move an application to another core, because we're going to have too much overhead for steering all the requests to a different core. And as a very brief overview of the steering algorithms, for request steering, we just check if the load on the local core is below a threshold. And if so, we can just queue as normal, that's okay. But if it's above some sort of threshold, we find a load of candidates from the other cores, which have a load below the threshold, and then we just randomly pick a core at the end and then move the request there. And the load on the local core and the threshold is defined by the sum of the outstanding bytes at the device queue, so how much backup there is. The second one for application steering, it's a little much to read on the slide right now, but the general idea is that we want to steer latency sensitive apps and throughput sensitive apps away from each other. So we want to spread them across different cores if possible. So for the evaluation, they use 2 servers connected by a fast network. And in the evaluation, they present results for in-memory storage and disk storage, but almost every experiment is for in-memory remote storage. And they have 3 reasons for this. The first is that when they're using in-memory storage on the second machine, they can generate a load close to the network capacity, just a higher load. And when they use an NVMe SSD for the tests, even though the NVMe SSDs are fast, it only takes about 1 or 2 cores to saturate the device completely. So testing scalability with a lot of cores, it's kind of hard when we're saturated with 2 cores. And finally, when they test on an NVMe SSD, even though it's low latency, the access latency is high enough that it could hide some of the benefits of the scheme and be hard to reason about if it's better or not. And in general, for the tests, they just vary the amount of latency sensitive apps and throughput sensitive apps while carrying out random reads. So for the latency sensitive apps, we have small requests and then large ones for the throughput sensitive apps. So the first sort of goal or ideal situation for this scheme, what they wanted to achieve is low latency and high throughput at the same time. So if we have 2 graphs here, if we look at the bottom right graph first, what we have in the test is we're running 6 throughput apps, so 1 for each core, and then we vary the number of latency sensitive apps. And then we look at the total throughput in gigabytes per second. And we see as we vary the number of latency, as we increase the number of latency sensitive apps, for SPDK, throughput drops pretty sharply, but for Linux and block switch, it stays very high. But even though the throughput for Linux doesn't decrease, if we look at the top graph on the left for the single threaded case, which applies to this graph at the bottom, the P99, so the tail latency of the Linux scheme, is over 10 times that of the block switch scheme. And the reason for this is that just what we discussed from the techniques they introduce. So the first is that the block switch modification allows us to distribute requests to underutilized cores at that point in time, instead of these latency sensitive requests being blocked by throughput requests. And the application steering allows us to effectively separate latency and throughput sensitive apps to different cores, so there is less contention at the device queues. So the second thing we want to look at is what is the performance, or how does the performance change when we vary the load from the throughput app. So in general, a higher load will lead to higher contention, which just increases the problems this paper is trying to solve. So if we look at the graph, the top right graph here for latency, excuse me, at the bottom, so what we're doing is we're varying the I/O depth of the throughput apps. And a higher I/O depth just means more throughput. So we look at the latency, and for Linux and SPK, the latencies are increasing as the depth of the throughput apps increase. So higher load is higher contention because of things like head of line blocking, as we discussed earlier. For block switch, as the load increases from the throughput apps, latency stays the same or even decreases for block switch, which is what we want to see. And if we look at the total throughput, so as we increase the I/O depth of the throughput apps, block latency, or excuse me, block switch, it's keeping a low latency, but at the same time, throughput is increasing. The throughput increases for all of the schemes because the I/O depth is increasing, but for block switch, the latency doesn't increase or barely increases at all because we're able to effectively separate these apps between cores or steer requests to underutilized cores, reducing contention at the device queues. And we'll notice even though block switch, we're achieving low latency and high throughput, but it's actually slower than Linux by about 10%. And that's just due to the overhead of steering applications and requests introduced by block switch. So to conclude, it's kind of hard to achieve this microsecond scale latency in the current storage stack for the Linux kernel, as they argue. And a sort of general way to describe the problem is that these latency sensitive applications compete with throughput applications for slots and queues, which causes higher tail latency. So in this paper, they introduced this block switch addition or modification to the block layer, where they make the block layer look like a network switch, and we can steer requests and applications to different cores. And the results are pretty good. We can say it effectively balanced load across cores while achieving microsecond tail latency, at least across the tests they did in the paper. That's the end of the presentation. Thank you.